then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, Precalculus students, and welcome to Lesson 1. So Lesson 1 is an introduction to functions. Now, I am quite aware that you have been exposed to functions in Algebra 1 and in Algebra 2. And you might wonder, why are we talking about functions yet once again? So perhaps you were never informed about the importance of functions and the role they play in something called mathematical modeling in real life applications of mathematics. So I want to talk a little bit about that before we get right into it. So many things in life can be simulated or modeled with mathematical equations or mathematical functions. And these mathematical functions allow us to do a lot of useful things in the world. For instance, lately we've been dealing with this COVID-19 deal, and you'll see on the news where they make predictions about the number of people that are going to die or get infected, which is very useful information. Of course, this information is calculated by mathematical models. There's a function. The basis of the function in this type of math is something called an SIR model, but it's basically a function. It's really a differential equation, which allows us to precisely predict complex information like the number of people to get infected or die from infectious disease based off a variety of factors. Also, how fast your car goes when you press down on the pedal. There's a mathematical function determining that. The fact that I'm giving this lesson on the second floor of my house without any fear that I may collapse and fall to the bottom at any time is my confidence in the scientific mathematical models or mathematical functions that gave the structural integrity of this particular building. So these functions are all around us, everywhere you go. It's almost ubiquitous. You'll be hard pressed to find a scenario in life where there wasn't a mathematical model or some mathematical function used some way in that particular outfit. That's how common it is. So that's why it's important. So some of you, not all of you, of course, but some of you are going to go and use math in your profession. You're going to have a profession which is based off applications of mathematics. And most of what you're going to be doing is you're going to be using functions. Of course, very intricate and complex functions, but very beneficial functions to solve problems that the world sees. So that's why we use functions and why we talk about functions so much. And we'll also talk about functions. If you're lucky enough to get to calculus, there still will be a discussion about functions. They play a pivotal role in upper level mathematics for a very long time. So with that said, let's go ahead and get into lesson number 1. Now, I just talked about how we use mathematical models. So what better way to introduce functions than with a scenario that can use a mathematical model or a function to simulate that scenario. So my first scenario is as follows. A person standing on top of a building drops a sandbag from 80 meters above the building. That's my scenario. And what you see now is a table. And so in this table, I'm going to put some data. So there you see the first column is time, and this is time in seconds. And what I'm going to do is record the velocity and the height at certain values for time. And I'm going to use when time is 0, 1, 2, 3, and 4 seconds. So those are the values of time I'm going to use. And I'm just going to record the velocity and then the height. I'm going to record the velocity first because it's an easier number to get, and the height is just a slightly bit more complicated than finding the velocity. So I'm going to find the velocity first, and then I'm going to find the height. And once I fill the data in this particular table, I'm going to look at finding this same data with using a function. And you'll see the benefits of using a function in a scenario such as this. So the person is dropping this sandbag 80 meters above the ground. Now, for this particular situation, we're going to disregard air resistance. So there's no air resistance in these calculations. So the only thing acting on the sandbag for our scenario is gravity. Now, the acceleration due to gravity is negative 9.81 meters per second squared, or negative 9.81 meters per second. A lot of times in math, we graciously round that number for easy mathematics. So I'm going to round that figure for the acceleration due to gravity on the planet Earth to negative 10 meters per second squared, or negative 10 meters per second. So that's the figure I'm going to do. It just makes the math a little bit easier, and we can get these calculations quite quicker. Okay, so the acceleration due to gravity, we're using negative 10 meters per second. And I like to say it meters per second, so you understand what that means is every second the velocity is decreasing by 10 meters per second. Every second the velocity is decreasing by 10 meters per second. And that's why the acceleration is negative 10 meters per second. Okay, so let's talk about at time t equals 0. So time is abbreviated in mathematics with the variable t. So a lot of times when I refer to time, I'm going to refer to it as t equals something. So first we want to look at the time when t equals 0, and now we're only looking at velocity. So what do you think the velocity is of this sandbag at time t equals 0? And of course you should have said 0. So at time t equals 0, the sandbag has yet to be dropped. It's just about to be dropped. And so there is 0 velocity occurring. But now what happens at time t equals 1? So at 1 second, what should the velocity be? Now again, remember, the only thing acting, I said sandbag. The only thing acting on this sandbag is the acceleration due to gravity. At time t equals 0, the velocity was 0. At time t equals 1, the velocity should be negative 10. Again, the acceleration is negative 10 meters per second. So every second, again, the velocity is going to decrease by 10 meters per second. And so with that understanding, it should be very easy to know that at time t equals 2 is going to be negative 20, t equals 3, negative 30, t equals 4, of course, negative 40. So those are the velocity. And the velocity is a vector quantity, and we'll get into vectors a little bit later, quite a bit later. But I'll say this, a vector quantity gives you direction and magnitude. And for something like this, this type of motion, a negative velocity is an indication that the object is moving downward, and a positive velocity would be an indication that the object is moving upward. Of course, in this particular scenario, the sandbag is only moving down, and that's why all the velocities that you see here are negative, except for, of course, the initial velocity at time t equals 0, which is neither negative nor positive, which is 0. Okay, so we have our velocities. Now let's find the height. Let's find our heights. Now, of course, at time t equals 0, the height would be 80, because that's where it was. So that's not that significant of a question. The good question is, well, what's the height at time t equals 1? So I really want you to think about this. This is a very important question. And pause the video if you need a few moments to kind of think about this, because this is something that you really want to think about. What is the height at time t equals 1? So again, pause the video if you need time to think, and then I'm gonna walk you through this. Now, let me tell you the most common incorrect answer to this question. The most common incorrect answer would be to say the height at time t equals 1 is 70 meters above the ground. That, of course, is incorrect, but it's based on good logic. So those that say that, they're basing it on the fact that the acceleration is -10 meters per second. And since the velocity at time t equals 1 is -10 meters per second, they are only assuming that it must have moved down 10 meters in 1 second. The only thing, what's making that wrong is the fact that from 0 to 1 second, the velocity was not -10 the whole time. If it was -10 the whole time, then it would have definitely moved down 10 meters. But since it went from 0 to -10, it doesn't move down the whole 10 meters. So how can we figure out how far it moves down? Well, probably the easiest way to explain it would be through physics. And let's just deal with some basic elementary science. So in science, you learn that distance equals rate times time. Okay, so in this case, the distance is, the height that it's going to travel, how much it's going to move. In physics, they call that displacement. The rate, that would be the velocity. Now again, you have a changing velocity here from 0 to -10. So you're going to need to get the average velocity, and that would be the initial velocity plus the final velocity divided by 2, the average of those two. And then of course the time here is just 1 second. So we have this formula in physics where delta x is 1/2 v sub I plus v sub f times delta t. That delta x stands for displacement. If you haven't been exposed to physics, displacement is very similar to distance. Technically, displacement is the distance from where you started to where you ended, and that could be different from a distance traveled. However, when you don't change directions, so in this case, the sandbag is only moving down. When you don't change directions, distance and displacement are the same. So think of displacement, if you haven't been exposed to this type of physics before, just think of displacement as distance, because in this case, it's exactly the same thing. And of course, when you see the 1/2 v sub I plus v sub f, well, that's the average velocity. It's the initial velocity plus the final velocity divided by 2. And then of course, you times the delta t, because again, distance is rate times time. The rate is the average velocity, and delta t is the time interval in the situation. So let's go ahead and calculate the number for what we have here. So our initial velocity, and we're looking at time t equals 1, so we're going from 0 to 1. So the initial velocity is 0, the final velocity is -10, and of course delta t, or the time interval, is just 1. So we have -10 times 1/2, essentially, so that's -5. And -5, so that's the distance traveled from 0 to 1 second. So after 1 second, it's traveled -5 meters, or 5 meters downward. So that means the height at time t equals 1 would be 75. So, and if you follow, that may, when I showed that physics formula, it might have seemed complicated. But with this particular scenario, it's quite easy, primarily because our delta t for all our intervals is going to be 1. So really, for all of these, all we have to do is find the average of our velocities and add it to the given height, the previous height, and that's going to give us the new height. For instance, for what we just did, we could have just took the average of 0 and -10, which of course is -5, and added -5 to 80 and got 75. So just to continue on like that, for time t equals 2, I'll add -20 and -10. That's -30 divided by 2 is -15, and -15 plus 75 is 60. For time t equals 3, it's -30 and -20. That's -50 divided by 2 is -25. Negative 25 plus 60 is 35. And then lastly, for time t equals 4, we'll do negative 40 plus negative 30, that's negative 70. Negative 70 divided by 2 is negative 35. And negative 35 plus 35 is 0. So that means at time t equals 4, the sandbag has hit the ground. Okay, so that was not the hardest thing in the world to do, but somewhat drawn out to have to calculate each of these things in this piecemeal way like this. And just let's suppose we were dealing with an object dropped a lot higher than 80 meters that's not going to hit the ground in 4 seconds. Let's say it hits the ground in 3,000 seconds. Or let's say you want to know its height at time t equals 1.35 seconds for a particular reason. So that's just saying that this tabular way of finding particular heights and velocities is a bit much. And if one could find a function that simulates this scenario, we call this scenario free fall. If we can find a function that simulates this free fall, we can find these particular values quicker. And we are aware of such a function. So I'm going to introduce that function to you. And this function is to find the height. So I'm going to give you the function that will find the height at a given time t, not the velocity. I mean, there is a function to find the velocity. It's a very simple function. And so it's so simple, it's not even worth looking at. I mean, just look at your velocities compared to your time t. It's just the time times negative 10. In fact, the velocity function for this is just negative 10t. So that's not, it's not very intellectually stimulating. So we're not going to find a function for velocity. We're going to find a function for height. And that's going to be a pretty simple function as well, but it's not as simple as velocity. So it's a little bit worth our while. So this is the position, we call it the position function for free fall. And what it gives us is it gives us the height of the object in free fall at a certain time t. So this function depends on t. So t is the independent variable. So in many real life mathematical equations, not all, but in many, time is indeed the independent variable. So t is in many cases the independent variable. When we're just doing, abstract problems, we like to use x, but in many real life problems, the independent variable is t. So it's a variable you'll see a lot. You may see t in this course more than you see x, but you can see any letter in the alphabet depending on the scenario, of course. So just to go over the function, and I wrote the function in y equals form, and I did that just to stress upon you the importance of the function notation form, which I'm going to switch to in a second. But the function is 1/2 g times t squared plus y naught. So y equals 1/2 g times t squared plus y naught. So I want to tell you what each of these variables represents. So y, our dependent variable, represents the height. And g is a constant. G is the acceleration due to gravity, which we're using negative 10 meters per second squared. T, of course, is the time in seconds. And y naught is the initial height in meters. I should make mention that when I use this negative 10 meters per second figure, that's a figure I'll use for acceleration due to gravity when the measurements are in meters. If the measurements are in something different, say for instance feet, then there's a different figure. It's negative 32 feet per second squared. So the negative 10 we'll use is when the measurements are in meters. If it was in something other than meters, there would have to be a different measurement that we would have to use. And so this is the function, and I want to put it in function notation. So instead of y equals, I want to put f of t equals, just to briefly explain the significance of this function notation. Again, we make these functions to simulate physical phenomenon in the real world. And of course, we have to evaluate these functions at different values for different things, depending on the problems that we need to solve. And so, for instance, the function we had, maybe it was very important to me to know the height at time t equals 3. Well, I can show that in a notation as being f of 3. So f of 3 equals whatever f of 3 was. So writing in that notation, f of 3 equals, is a very efficient way of showing this is the value of this particular function when t is 3. So that notation is a lot better than just the y equals notation. The guy in the parentheses, which makes it function notation, which is pretty important because it gives us a strong indication when we're evaluating the function at different values of what values in which we're evaluating the function at. So I just want to go ahead and plug in, what 1/2 g is. So again, g, I'm using -10, so 1/2 of g is -5. So my equation for this particular case, and my initial height for this case was 80. So my particular equation for this scenario is -5t squared plus 80. And now I'm going to use this function to find the heights that I've already found in that table, and just to show you that I get the same values using this function as I did, kind of using the physics deal that I used there. So let's first find f of 0. So we're plugging in 0 for t, and you can see that -5 times 0 squared is just going to be 0, so we get 80. And that's the same that we got in our table. We got 80 for the height at time t equals 0. So let's find f of 1. So we find f of 1, which is -5 times 1 squared, which will be -5, and a -5 plus 80, of course, is 75. Same measurement we got in our table. And if we look at f of 3, so that's 3 squared, which is 9 times -5, which is -45. -45 plus 80 is 35, as what we got in our table. And lastly, f of 4, 4 squared is 16. 16 times -5 is -80, and -80 plus 80, of course, is 0. Again, the same measurement that we acquired in our table. So again, that's one indication of how a function can simulate something in the real world, allowing us to get very quick calculations for whatever value we want to plug in. So I want to look at another scenario, and so for now, we'll introduce and you will discover various functions through the course of the class that simulate different physical phenomena. But right now, the one that you're aware of is the one for free fall. So the free fall function for any scenario is going to be -5t squared plus whatever the initial height is. Of course, if the information is given in meters, and really everything I'm going to give you is pretty much going to be in meters. There may be a couple times I give you something in feet, and if ever I do, then I'll make mention of the change to -5 to -16 of the 1/2 g. But for the most part, you're going to be dealing with -5t squared because the stuff is in meters. So in the second scenario, a ball is dropped from a height of 20 meters above the ground. How high above the ground is the ball at 5 seconds? So pause the video and see if you can solve this question. When you unpause it, I'm going to work the answer out. Okay, so it says the object was dropped 200 meters above the ground. So that means that the position function for this particular scenario is going to be that f of t is -5t squared plus 200. So a pretty easy function to remember. And they want us to find the height after 5 seconds, the height at 5 seconds. So that's just finding f of t. That's finding f of 5. So f of 5, and of course to find f of 5, I'm just going to plug in 5 for t, and -5 times 5 squared plus 200. So that's -5 times 25, which is -125, and -125 plus 200 is 75. So at time t equals 5 seconds, the object is going to be 75 meters above the ground. So that's pretty simple. So in our introduction to functions lesson, we introduced or we touched on how we use functions to simulate physical phenomena. Well, not just physical phenomena, it's also used in business to make certain type of predictions, and in many other fields outside of physical phenomenon. mathematical modeling via functions is used. So, but what we show today is just one indication of it when used to determine free fall. And in determining this free fall, we did something called evaluating functions, of course, plugging in different numbers to evaluate the functions. So I just want to do a few kind of abstract examples of evaluating functions. These functions are not simulating anything in particular. We're just kind of going over the very simple process. And I do understand this is simple of evaluating functions. So let me use something abstract. So I have some function f of x, and say f of x is a negative 10x squared plus 5x minus 13. So I have there's my function f of x. You see it in all its beauty. And let's say I want to do something as simple as finding f of negative 2. Now, of course, to find f of negative 2, the function is f of x. And what I'm doing is I'm replacing this x with a 2. So what I'll do in the function is replace every x with a negative 2. So this is negative 10 times negative 2 squared plus 5 times negative 2 and minus 13, and we kind of just do our operations, our little arithmetic here. I'll do exponents first. So negative 2 squared is positive 4. Positive 4 times negative 10 is negative 40. And here 5 times negative 2 is negative 10. And then you got this negative 13, so that's negative 63. And just to do another example, I understand this is easy, but there are many things in mathematics that are very easy to do, but very important in principle. So this is one of those guys. So let's take another function. Let's say the function is h of t, where h of t is 100 minus t minus 2t cubed. And let's say we find something is simplistic, but maybe as crazy as h of 8. All right, so we're going to find h of 8. And again, this function listed is h of t. And what I've done is replace this t with an 8. So what I'm going to do in this function, everywhere I see a t, I'm going to plug in an 8. So this will be 100 minus 8 minus 2 times 8 cubed. So this is 100 minus 8. Let's just call that 92. And this is 2 times 8 cubed. 8 cubed is 512. So that's 1024. So this is 92 minus 1024. And so that's going to be negative 932. Negative 932. Make sure that's accurate. Just a quick check. Add these, see if I get my 1024. That's 4, that's 2, that's 20. Yeah, so that's negative 932. Okay, so again, you'll see that's pretty simple. But lastly, in this lesson is almost complete, I want to introduce a couple other things of evaluating functions. So say we have the function g of t, and g of t is t squared minus t plus 9, and say I want to find g of r minus 6. So, and this is something that will come up where we want to evaluate functions with a variable expression or an algebraic expression versus a numerical value. It happens, folks, so we have to be able to deal with it. But again, the same rules apply. This function is g of t, and what I did is I replaced the t with r minus 6. So everywhere I see a t in a function, I'm going to replace it with r minus 6. So this is r minus 6 squared minus r minus 6 plus 9. And I'm just going to do the algebra from there. So I have to square first. So if I square r minus 6, that's r squared minus 12r plus 36. And very important to remember this negative sign here, or this minus sign, applies to everything here in parentheses. So it's going to be minus r plus 6, and then plus 9. So I don't want to overlook this part here, because this is where a lot of mistakes occur. A lot of people would have put a minus sign in front of r, but kept minus 6. And again, this minus sign is applied to everything in the parentheses. We change the sign of everything in the parentheses. That's very important to remember. But from here, of course, we're just going to combine like terms. We have a negative 12r and a negative r. That's going to give us negative 13r. And we have 36 and 9. That's going to give us 45. So our final answer is r squared minus 13r plus 45. Now, in the midst of doing this problem, I am quite aware, I've been doing this for a while, I'm quite aware that some people may have struggled with the fact that r minus 6 squared is r squared minus 12r plus 36. In fact, every year I get a lot of people that struggle with this. Now you notice how fast I did this calculation. I wasn't showing off. We want to do calculations like this very fast. So this operation is something called squaring binomials. And this is something we want to be very good at, because these things pop up a lot in this course. They kind of pop up like a Pop-Tart, cinnamon brown sugar, the kind with the frosting. So it's something you have to be very aware of. And if you're not aware of this whole deal with squaring binomials, I just put a link up. So there's a link in the top of the screen for a short video going over the whole process of squaring binomials. And so that's something that you need to freshen up on. Watch that video and it should bring you up to speed. Other than that, that's going to complete our first lesson, folks. I hope you enjoyed it as much as I did, and we'll see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe-to-toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.